First exercise. So define the function mi star of any set A is equal to the outer Lebesgue measure of M star A intersection E, where E is a measurable set with respect to Lebesgue. Okay? So, first question. A. Is mi star an outer measure? So, well, we justify. Just say yes is not an answer, no?
Is the question.
Huh?
Is the question.
Yeah, but okay. Justify, that will be written somewhere. You have to justify your answers. So, which are the measurable sets? But clearly, if you say no to the first set, it's like it's done. To which measure it corresponds? How does it correspond? When, okay, restricted to the measurable sets. It's sigma algebra, okay, of measurable sets, doesn't matter. Okay. So I see from here that you have to solve at most 5 exercises out of 8, so you can even choose. And the points are very generous. For example, here it's 8. And I think that I have to check what is the ranking metrics, but okay, it's more is probably 1/5 of what you can get. Okay, so easy, no? This is easy. So is mi star an outer measure? Yeah, yes. Otherwise you end. But okay, why it is an outer measure?
Because of the following question.
Okay, it's just simply M star restricted to some particular sets. So the subadditivity, well, you just need the subadditivity of M star on this class of sets, which are subset of E. So A, okay, 3, it's elementary, no? So mi star is outer measure. And then, okay, sorry, M star is an outer measure, then mi star of the empty set is clearly equal to 0 because it's M star of the empty set. And mi star of any union of AI, that by definition is M star of the union of AI intersection E. This is an outer measure, so less or equal than the sum of M star of each of these sets. And by definition, this is the sum mi star of AI. Okay. Questions here?
Yes, can we write like this in the exam? I mean, without specifying the AI, just
Yeah. Yes. Okay. If you consider trivial, but then if I discover that you make a mistake because you consider trivial is -2 points. So if you try and make a mistake, it's -1 point. If you say it's trivial and then you make a mistake, it's -2. Okay. Well then, which are the measurable sets? This is a little bit tricky.
Sets that the intersection with A are measurable.
Yes, incredible. It's true. Okay, so how to verify that?
By definition.
By the definition, yes. Okay, let's do the definition. So let's say f is measurable. So I have to require that mi star of for all A, mi star of A is equal to mi star of A intersection F plus mi star of A. Okay, so well, this by definition is M star A intersection E is equal to M star of A intersection F intersection E plus M star of A minus, so it's A minus F, so it's A intersection E minus F. Okay, so it's okay, let me think. Oh, this I think I wrote something which is better like this, no? F. Okay, no, it's correct. Okay, let me see now, because I want to say that every intersection F should be measurable, no? Is M measurable. Okay, so, well, and this is equal to M star A intersection E intersection F intersection E, because plus M star A intersection E minus, again I need just F intersection E. What is outside E doesn't matter. So I deduce that if this guy is measurable with respect to Lebesgue, well, this clearly holds. I discovered that from this declaration I discovered that if F intersection E is in M, then it is mi star measurable. Okay, but now I have to do the opposite part, because I want to prove that they are exactly these guys. So far I just proved that these guys are mi star measurable. B, there are others. Okay? So, okay, so, so let me see. So this is the, from this I deduced this guy holds when intersecting this guy. Okay, but then I have that if F. Okay, because it's immediate, and then I have to think how to prove it.
we can use the fact that it is measurable
Yeah, to say that the intersection is yeah, okay, yes. Because I use the relation that m star of E of A is equal to m star of A intersection E plus m star of A minus E. Because E is measurable. Okay? So now, if I give you F, so now I have a set for which this holds, and then I have this holds, so I rewrite m star of A intersection E intersection F intersection, okay. So because I'm taking a set so that the intersection is measurable. E plus, so I'm using this relation, which now I assume. Because first I say I want to have this relation and then obtain that. It implies this guy. Vice versa, now I assume it holds, I want to say that it implies this guy. So these two things are equivalent. So if I assume this relation, just replace this with this guy here. Okay. And now, since I assume, let me think how to add the stuff. Now I need to add something. So if this is, let me see where to add. This is A minus E plus the intersection. Okay, I think this guy here, I add these two. So it is A minus E intersection F intersection E. Sorry, I get lost.
The first term is the first part already of M star of A decomposition.
See, because I want to prove that if this holds, so this guy, if I require this assumption, this tells me that it's, sorry, this morning it was hard. Okay, so I assume that this should hold. So if I satisfy it, I rewrite the thing, I get this relation. This relation tells that if this guy is measurable, then it holds for all these guys here. So it's verified if this is measurable. Vice versa, assume that it's measurable, so I have this relation here, okay? And then I want to prove that the intersection is then, sorry. So I assume that it's measurable, I want to prove that this holds, which is trivial. I don't see what is the problem.
I think we can write the composition again of.
I knew I had to do this, yes.
I mean with immeasurable again with A minus F. And this gives exactly the
yeah, because I know that you have to do one of these decomposition twice, but this morning I'm a little bit sleepy, I don't know, sorry. And I'm sorry, I have to get the thing done by my. Okay, so here I have that if this method, vice versa, if this hold, okay, so I use this here, then I can add this guy, and then I want to write it in E intersection minus F, because I have this relation here. Okay, and so this is E, this is F, and I want to say that so I want to rewrite this as M star of A. So this guy is F intersection E. Yes. And now I have E minus F plus M star, so it is this guy, plus what is left outside. Yes, and what is left, this two sum is M star, because this guy is measurable, so it's M star of A minus F. Okay, so, okay, and that's it. Minus F intersection E, sorry. Just this part, just this part. I'm sorry, I was confused. You have to add these two parts. And you make drawing and then you discover. So this part says that if you assume this relation, then you deduce that the intersection is measurable. Because you get that for every A, these two. It's okay, I'm sorry. Okay. To which measure does it correspond? So let's take a set which is outside A, outside E. What is the measure? It's 0, no? So, and if for a set inside E, is the Lebesgue measure of E. So okay, and then put the thing together. No, I'm asking what is the measure? Mi is equal to the Lebesgue measure restricted to E. Okay? Because you write, so mi of any set, let's say F. Okay. F now is measurable. So it's mi F intersection E plus mi F minus E. And now you apply the definition. So here, this is equal to M star, because is mi restricted to the set. So it's equal to M actually. And this is 0 because you use just this definition. If it is outside E, mi star is 0. Okay? So the only tricky part is the point 2, that you have more measurable sets, simply because you have a set which is 0, and any subset of that set is measurable for me, but not for M. Okay. I think I really understand people are tired, because I'm tired of this. Oh, exercise 2. Prove the following. A. F Lipschitz. Okay, when it is not specified, we are in R. F is absolutely continuous. B. F absolutely continuous, then F, the Lebesgue measure of f of n is equal to 0 if the measure of n is equal to 0. These are just classical. Okay, C. Okay, give say phi from R to R as usual, such that point B does not hold. But this is theory, no? Let's see. Okay, let point A. So everything is about absolute continuity. So what is the definition? Start with definition. If the map set of value 0 and measure 0 is the same. If you want to say it is something short, you say if map sets of measure 0 into set of measure 0. Yes. It's the short way. Okay. If, and then you rewrite it in terms of epsilon delta. For all epsilon, there exists delta, and then if I are intervals of measure, this joint, let's say this joint, such that the sum of the length of the interval is less than epsilon, finitely many or countably many doesn't matter now, so at the end it's finitely many, but we know we can pass to countably many. The sum of the length, well, okay, it is at least continuous. So let's say it is at least continuous. Otherwise, I say sum of f. So these sets are AI, BI, BI minus f of AI is less than epsilon. And now, since it is continuous, I can replace this like the measure of the image of the intervals, which are intervals, or even I can even forget. Okay, so with this definition point A, so what is the definition of Lipschitz? F Lipschitz if, okay, the f of x minus f of y less or equal than Lx minus y. And now the L is L Lipschitz, just to remember the Lipschitz constant. Okay, so now the thing is clear. Point A, which is the choice? Delta epsilon over L. Okay, at least, but you can write this. I think I can accept because I'm not pretending that. Of course, the thing is that is at your own risk. Because if you write the definition, you make a mistake, I say, okay, he knows the definition, but he made a mistake. But if you just make a mistake, I cannot decide if you know the theory and then you just, okay, but this is it. B, that guy. That guy was also, I think, one of the results that we had, no? Okay, so take any set of measure 0. So the image is, well, it's covered by, so let n be m of n equal to 0. Well, first of all, the thing is that, okay, here we take finitely many, but even countably many. Because countably many, well, the sum converges, and if this sum is less than epsilon, this sum is less than delta. This sum is less than epsilon for every I, so the sum even to plus infinity, no? By definition of summation. So if it has measure 0, then for all delta, for all epsilon there exists, I take the delta, the O open, n is a subset of O, and the measure of O is less than that delta. And then this implies, okay, and here is again, how the definition is f of b minus f of a, but I can use this guy here. Because the image, well, first of all, it is continuous. The image, you just restrict the interval, no? The maximum and minimum are inside, you take that value, you diminish this sum, and still you have the same value. Okay, so from that guy, it tells you that the image, the measure of, well, and this guy, so I take the union of, okay, the f of the union, which is less or equal than, okay, the sum, because, okay, the f of the image is less than the union of the image, and then the union, it might be, is not disjoint, who cares? At least you get the sum of m of I, and this is less than delta, this is less than epsilon. So for all epsilon, I take an open set, which contains my set, whose measure is small. Then I apply the definition. The definition tells you that the measure of the image is smaller than epsilon. So result, this set should have measure 0 because I have an open set of arbitrarily small measures. So point C. Okay, we basically there exists only one function, more or less. Which is more, in some sense, is true. I mean, you can, of course, you have all the transformation you can do, but at the end, the example is that. Okay, which will be the function? The standard Vitali function, yes. So so phi is Vitali. David, Cantor, David, whatever you like. Step.
A question.
Yeah.
When we say the point B does not hold, we mean this implication that we just proved? Or?
So there exists a function, yeah, okay, I just shortened the thing, which maps a set of measure 0 into a set of positive measures. Yeah, it's this one. But I just shortened, I didn't want to write the sentence. Okay, Vitali staircase. Yes, it's correct, because what we know is that the image of the Cantor set, the 1/3 Cantor set, okay, is equal to 0, 1. And the measure of this set is 0. The measure of K 1/3 is equal to 0. Now we know also that the Hausdorff dimension is 1/3. So the dimension Hausdorff of K 1/3 is equal to 1/3. Okay. Nothing. Oh, this is difficult instead. My suggestion is before doing any exercise, you read all the text carefully and select the one that you are sure you can solve. No? Because the standard, you start with something, then you can know, you discover you don't, then you do that, then you just lose time. do like this and then you're fine. Okay, we have to prove the Riemann Lebesgue lemma which is f is in L1 in R, okay, so it's from R to R in L1, then the limit for alpha which tends to infinity, well, it doesn't matter in which sense, integral of f of x, I alpha x, I is the imaginary unit. So this is like something like cosine of alpha x and sine alpha x. Okay, this guy is equal to 0. By the following steps. I'm not attempting to invent the proof. And then it is continuous. So, and then this is a continuous function. A. Okay, we need to use one theorem. So the suggested use a passage to the limit theorem for continuity. B. Limit is equal to 0 true if f is the characteristic function of E bounded interval. So let's call it I bounded interval. General case by approximation. Okay, there are sometimes there are some in exercise you have some bonus if you want to get more points. We don't see the bonus, we see just the okay, proof. Okay. Which theorems are we going to use here? Well, we know there is, of course, there is one it works in the general case because it's the most general, which is Vitali plus tightness theorem, no? But okay, here, whatever theorem you use, at least you have to verify the assumptions. Okay, so I want to prove that the limit for alpha which tends to beta fx
that's for the continuity of the function in respect to alpha.
This is a function of alpha, no? Which is usually the notation is f at alpha, the Fourier transform. Like up to some normalization constant, because okay, if you want to preserve the L2 norm or whatever. This is the Fourier transform. So why is that true? Lebesgue convergent theorem. Because f of x alpha x is f of x, and this is an L1. So all these functions are bounded by an L1 function, so you can pass to the limit. Continue. B, how to prove that these hold? You compute. Okay, this I leave for you because it becomes 1 over alpha. So for the integral from a to b of e to the alpha x, whatever is 1 over alpha something. And then general case. By approximation. So we know for intervals, and then well, this should suggest you the approximation. At the end there is only one approximation, which works, because it's the way you compute everything. Simple functions. So f is sum, and then, okay, here I should put, okay, so there is an intermediate step, no? Which is?
Prove that it works.
So I need first f equal characteristic function, sorry, of some interval, some set. Okay, so how to do for set?
It is the symmetry difference.
E is equal to a finite union of intervals plus, okay, or plus or minus, whatever, some set, let's say some E prime, and the measure of E prime is less than epsilon. Well, and then once you do for that, the proof for F will be the same. So let's do. I can start with the main estimate, but let's do for this guy, and then you understand. So now, let's compute the integral. Okay, now it is the sum of some, well, open intervals. I should say that it is plus E prime is equal to this guy plus another one. But I don't want to enter because otherwise I don't finish. So let's say E is essentially like some intervals, and then I have some piece. So this guy is the integral over these intervals I plus I have the integral of what is left, which can be positive or negative because I add some part and then I forget some other. But its integral is small. So now if you observe here, whatever is left, it's small. So here you have plus some constant, let's say 1, of times the measure of E ma, the symmetric difference of the union of the intervals. Now the formula is correct. Actually, here I can put without. So the integral by linearity, I take the main part and what is left is small, and magically, by this estimate, my error is uniform in alpha. Indeed, that you can use this uniformity to get another proof, which may be faster. Okay, so finally this guy is less than epsilon. So take the limit, lim sup of the modulus of this guy, okay, this is 0, and this is epsilon. For any epsilon I can do, so the limit is 0. And for general f, well, it's the same, because this estimate is uniform. Okay, it is a little bit long, maybe to write down, but okay, I don't have I don't like evaluating what exactly it is written like a machine. I prefer that if I understand that you let me understand that you know how to adapt the proof, I believe. Unless, well, in that case it's minus 2 points. Okay, another one. This is a classical lemma you will see everywhere. I suppose you have this exercise in the tutorial, but let's see. So Fn is a sequence of positive functions, and Fn converges to F almost everywhere with respect to the back. And F is less than plus infinity. So I know that the limit is integrable. Prove that in general, well, of course, in general, the integral of Fn is less than the limit of the integral of Fn. Okay, which is, well, fatto is less or equal than particularly you don't require the whole. Assume that the integral of Fn is equal to integral of f, the limit, and prove that the limit Fn minus f is equal to 0. Now that I see that I don't understand the point here, but okay. Point A, but you just need to give an example.
Characteristic function of n
Has to be
and n
positive.
plus 1.
Hmm?
Go ahead.
F positive, yes.
Hmm?
No, you said F positive.
No. Characteristic function
Okay.
is not always positive.
Characteristic function, but here is, yeah, okay, doesn't matter. Let's say it's 0 plus infinity, I think. But doesn't matter. Well, you can always take one piece flow into the infinity. So
So
that's,
I want to say characteristic function of n plus 1.
yeah, it flows. But there is something in the proof because here it doesn't work. Let me see if there is some. No, okay, yes. Okay, assume now that the integral is converging. So, okay, so we take the characteristic function n plus 1, and then you're done. Okay, if you want to positive, just add any one function and it works. Okay, so point B. Assume now that the integral are converging and prove that they converge like this guy. Okay, let me think how to do that. Okay. Okay, so I just suggest half. So define Gn is the minimum between f and fn. And what is left? Hn is the max f and fn. Okay. So point B1 is that the integral of the limit over n gn minus f is equal to 0. Why? Is Lebesgue. Now let's take the other guy. So actually, because this guy is equal to f minus gn actually. Now let's consider the other, b2. So I want to consider what is the limit over n of the integral is hn minus f. Okay, this is a positive quantity, no? Is equal to the modulus because it's just maximum. Okay, and here I have to assume the integral converges because hn is equal to. So let me see. If I this is so I give you f, I give you fn, and this is hn minus f, and this is gn minus f. This difference is gn because gn is this point. So the difference, so I know that the integral of fn minus f, okay, these are two parts, so it's equal to the integral of hn minus f plus the integral of gn minus f. Okay. So now this limit here is equal to the limit of this guy minus the limit of this guy. But the limit of this guy is 0. The limit of this guy is the assumption, so I deduce that this guy is equal to 0. Okay, and then I have just to observe that fn minus f is equal to the integral of hn minus f plus f minus gn. And so the limit is 0. You like it. But don't, there are some suggestions. I mean, not in the text, but I think there are some suggestions. I think because there are suggestions because last year we saw these exercises during the course. Okay, let's jump about this. I don't like this kind of exercise because we have not much time. So let's see. This guy. Let's do this. Let's try this guy. I think this one is the one to do. So exercise 8. Let's end here because I think you're tired. I'm tired. And we do the other exercises are just application. Well, there is one where we. Well, okay, maybe we do also number 5. So let's start with this guy. Fn from R to R is a sequence of functions such that for all open sets. Well, I think I put some open set, doesn't matter. Open sets, bounded interval is the same. The lim sum of the integral of the modulus of Fn over O is less or equal than the integral over O of G. So G is positive. So A, prove that Fn is tight. Okay, and then find the interval and find an interval. Okay, I don't want to write the sentence. The interval means that I need to find a large interval so that what is left is less than epsilon for all n. So this is the short way. B. Assume that Fn converges to F almost everywhere. And prove that there exists K compact. Okay, here I put K epsilon compact. Okay, let's say this is I epsilon contained in I epsilon, such that Fn converges to F uniformly in K epsilon, and the integral over I epsilon minus K epsilon of G is less than epsilon. Okay, this is a little bit classical. Deduce, okay, so C, deduce that Fn converges to the integral of F, and F is less or equal than G. Okay, this is classic. Okay, so point A. Just the application of the definition of tightness, no? So for all epsilon, and actually the thing is that the second point you can restate like Fn is uniformly integrable. It's the same. And plus, sorry, because I just, the exercise is just messing up the uniform integrability, the Vitali and Sachs convergence theorem. Just messing up. But if you read, if you have that one in mind, you know the pieces. So the first is the tightness. The second is the uniform integrability plus Egorov. And the third one is that, well, okay, if it is tight and uniform integrable, it converges, and the limit should be less than G simply because G is the one that bounds everything. So, but this is not an answer, unfortunately, for you. So you have to do the computation. So for all epsilon, I want to have that the soup. So find the I epsilon of such that R minus I epsilon Fn is less than G. less than epsilon. Okay, see, so this is what I want. How to find this I epsilon? First question, can I remove here the absolute value?
Yes.
Yeah, I can. Why we get this guy? I'm not so sure. I'm not so sure. Because you have the oscillations. So let's keep the absolute value. Okay. So what is this I epsilon? It's given by G, no? So take I epsilon such that the integral of R minus I epsilon of G is less than epsilon. So by the assumption, then, there exists n such that for all n greater than n, the integral of fn to the modulus, even because I have the lim sup, that's another, so that you need to answer that, is less than epsilon. Because being the lim sup less, it means that some point is less than epsilon. And then, okay, so now, what you do, you enlarge epsilon, so for the remaining one, okay, for n equal to 1 up to capital N, you have this I, so this is R minus I epsilon n for such that the integral of R minus I epsilon n of f n is less than epsilon. And then you take the union. So I epsilon, the last one, let's say this is I epsilon G. I epsilon is the union of I epsilon n union I epsilon G. That's it. Right. So now let's do that. Okay, Egorov is fine. Because does not require anything, just that set is finite measure. But yes. So the only thing to add is that the epsilon you choose in Egorov is not related to F, but is related to G. You see, because Egorov, so let's cancel the thing. So Egorov tells you that so for all epsilon, you have to remove a set of measure epsilon. And then you have the uniform convergence. There exists a subsequence which converge uniformly. Okay? So now the problem is that here the epsilon should be related to G. But there are no problems here, no? Why? This is a subsequence. Otherwise it's false. So it's related to G. So now G is uniformly integral, being a single function. So I can decide, so I apply here with some epsilon prime, and I choose epsilon prime so that the integral over, let's say, I epsilon, k epsilon epsilon prime, the one that I choose here, of G is less than epsilon. It's the only thing. It's not requiring anything else. So just say that since the set I can remove in order to have the uniform convergence is as small as I want, I can choose this set to be as small as I want, and G being uniformly integral, since it is L1, can be less than epsilon. Okay. deduce that this holds, so I apply the Vitali theorem if I have the uniform integrability. Okay, so these two parts here should say that more or less it is uniformly integrable. How to do that? So what is the uniform integrability? Is the same. So it means that, well, we can say whatever we want. If I remove, so for all epsilon, I remove a set, let's say, let's call it O epsilon, such that well, okay, for epsilon, if the measure of the set O epsilon is less than delta, there exists delta, then the integral of Fn over O epsilon is less than epsilon. But let's have this set. Okay, so I need just to prove this fact, to apply the Vitali theorem. The theorem can pass, it is uniform, it is tight, point 1, and it is uniformly integral. So this one is the uniform integrability. Okay, so how to find this set O? It's already written.
We cut into two pieces. The first piece is already controlled by
Yeah,
epsilon.
this is already controlled. Because by the limit, I know that for as in the point 1, if n is sufficiently large, this controls this integral here. And then I have finitely many for 1 to capital N, but I know that finitely many functions are uniformly integrable. So what this set is this set minus, well, the part that I need to control for the others. Okay, so then I don't need to write it. As in point 1. Well, and I think